So if you step into a standard office elevator, the cables holding you up are engineered to be about 6 times stronger than they actually need to be.
Right, the safety factor of 6.
Yeah.
It's an engineering standard.
Yeah, exactly. You could pack that metal box with literal lead weights, and I mean, those motors wouldn't even break a sweat. It's incredibly heavy, it's massively over-engineered, and because of that, it's incredibly safe.
Which is exactly what we want for everyday life.
Totally. But if you strap into a rocket headed for space, that safety margin drops dangerously close to 1.
It has to, yeah.
Today, for this deep dive, we're pulling from this really fascinating masterclass in rocket propulsion engineering by Daniele Pavarin. And our mission today is to uncover the just mind-bending compromises, the chaotic physics, and the mathematical horror stories that make spaceflight possible at all.
Because it really is a horror story when you look at the map.
Oh, absolutely. So, okay, let's unpack this. Because the margins for error in rocketry are terrifyingly small, right?
Yeah, I mean, we love our Earth-bound vehicles to be heavy and over-engineered. We want that safety factor of 6.
Yeah.
But in spaceflight, well, gravity is the ultimate dictator.
Right.
And every single gram of material you add to a ship is a gram you have to fight to lift. Like, if you over-engineer a rocket the way you over-engineer a commercial elevator.
It's not going anywhere.
Exactly. We'll just sit on the launch pad. It will never leave the ground. So the entire discipline of propulsion engineering is basically a brutal, unforgiving war against weight.
And to fight gravity, you basically have to throw mass downward to push yourself upward. That's the core concept.
Newton's third law in action, yeah.
Right. And historically, engineers have built 3 different types of, let's call them throwers, like 3 different engine architectures to do this. We've got solid, liquid, and hybrid.
Which are all radically different beasts.
They really are. And to understand the sheer violence of this war against physics, we have to look at the anatomy of these engines, starting with the solid rocket, which, from what I'm reading, is basically a highly controlled pipe bomb.
That is actually a very accurate way to describe it. In engineering terms, solid rockets are the most straightforward architecture. You have this outer metal casing, and inside that tube, you pack a propellant grain.
But it's not like sand or powder. Right?
No. Imagine a solid, dense, almost rubbery mixture where the fuel and the oxidizer are already perfectly blended together. They cast this rubbery stuff with a hollow tunnel running right down the middle.
Okay, a hollow core.
Right. So when you ignite it, the fire burns on the inside surface of that hollow core, and it just burns its way outward toward the metal casing.
Which creates this brilliant, like, built-in survival mechanism. I loved reading about this. The unburned rubbery fuel actually sits between the raging fire in the center and the outer metal wall.
Yes. The fuel itself acts as the insulation.
It's a self-contained firework. It's dense, it's relatively simple, and it just burns from the inside out until it's completely gone.
And you can't turn it off. Once it's lit, it's lit.
Right, no turning back. But then when we look at liquid rockets, it sounds less like a firework and more like a terrifying high-pressure plumbing nightmare.
Oh, plumbing nightmare is the perfect phrase. Liquid rockets introduce just an entirely different level of complexity. You're dealing with separate, massive tanks for liquid fuel and liquid oxidizer.
And you can't just let them drip in.
No, you can't just open a valve. The inside of that combustion chamber is already exploding. It is a wildly hostile, high-pressure environment. To get the new liquid inside, you have to force it in with more pressure than the explosion itself is generating.
Which sounds impossible.
It requires turbopumps, which are essentially these incredibly powerful jet engines whose sole purpose is to just aggressively shove fluids down a pipe.
I was reading this part of a lecture, and I hit a complete mental wall. So you have this naked metal combustion chamber where the liquids mix and ignite, and the resulting gas is somewhere between 2400 and 3500 Kelvin.
Yeah, it's staggering heat.
Right, most of us don't think in Kelvin, but that is over 5,000 degrees Fahrenheit. That is roughly half the temperature of the surface of the sun.
It's hot enough to instantly vaporize most materials, yeah.
Exactly. So if you have a naked metal chamber full of fire that's hot enough to instantly melt any metal on Earth, why doesn't the engine just melt into a puddle of slag on the launch pad?
Well, you're touching on a massive pitfall there.
Yeah.
And solving it required an absolute masterpiece of thermodynamics. Engineers developed something called regenerative cooling.
Okay, how does that work?
So before that freezing cold, unburned liquid fuel is injected into the chamber to be burned, it is deliberately routed through hundreds of microscopic channels built directly into the metal walls of the combustion chamber itself.
This is where it gets really interesting. The freezing fuel acts as a coolant jacket.
Exactly.
It absorbed the catastrophic heat from the metal walls, cooling the chamber down just enough so it doesn't melt. And in doing so, the fuel absorbs all that thermal energy and preheats itself before it finally gets injected into the chamber to burn.
It is a perfect closed-loop survival mechanism.
Yeah.
You're using the very thing that will create the fire to protect the ship from the fire.
It's brilliant, just engineering jujitsu.
It really is. And then, sitting right between the solid rubber firework and the liquid plumbing nightmare, we have the hybrid rocket.
Right, the third type.
Yeah. This is where you might have a liquid oxidizer, but a solid fuel grain. So think of a cylinder of industrial plastic or like a paraffin wax.
So you blast the liquid oxidizer down the hollow center of that solid wax and ignite it.
Exactly.
But that has to completely change how the fire burns, right? Because they aren't pre-mixed like the solid rubber, and they aren't two liquids just smashing together.
It changes the combustion dynamics entirely. The oxidizer is rushing over the surface of the solid fuel. The heat melts and vaporizes the surface of the wax, and those vapors mix with the rushing oxygen in what we call a diffusive flame.
A diffusive flame.
Yeah, imagine burning a candle, but you're hitting it with a high-pressure hose of liquid oxygen. The flame exists in this really turbulent boundary layer where the two states of matter meet. It's incredibly complex to model and control compared to the other two.
Okay, so regardless of the architecture, you now have this massive contained fire burning at half the temperature of the sun. But heat alone does not equal upward movement.
No, it does not.
I mean, a bonfire is incredibly hot, but it doesn't just launch itself into the sky. So how does all that contained heat actually translate into thousands of pounds of thrust?
Well, what's fascinating here is the sheer scale of the microscopic chaos required to create macroscopic upward motion. The source material gives us this brilliant thought experiment to visualize it.
Oh, the particle thing?
Yeah. Imagine you are a tiny particle of gas, newly created inside that raging combustion chamber. You don't know you're part of a space program. You have no concept of a mission to Mars.
You are just a blind, superheated particle.
Completely blind and packed with immense kinetic energy because of the heat. You are bouncing violently, vibrating, and ricocheting in every possible direction, up, down, left, right.
Just total chaos.
Right, and now multiply yourself by trillions. Trillions of superheated gas particles slamming into the metal walls of the chamber simultaneously. This constant, violent, microscopic slamming is the physical reality of what we call pressure.
But if they are slamming equally in all directions, the rocket wouldn't go anywhere. The upward hits would be canceled out by the downward hits.
It would just sit on the pad vibrating.
Right, basically acting like a pipe bomb waiting to detonate.
The upward thrust only happens because there's a deliberate flaw in the design. There's a hole at the bottom of the chamber.
And that hole at the bottom changes the entire physics of the system.
Because the particles escape.
Exactly. The hot gas particles are slamming into the ceiling of the chamber, pushing the rocket up. They are slamming into the left and right walls, which cancels each other out. But at the floor, there is no metal wall to slam into.
So they just vent out. Right, they just escape out the open hole. Because you have a massive, violent push upward against the ceiling and nothing pushing back downward at the floor, the physical imbalance violently shoves the entire rocket upwards.
It's just an imbalance of microscopic collisions? That's so cool. But just poking a hole in the bottom isn't enough, is it?
No, definitely not.
Because the gas escaping out the bottom is moving fast, sure. But to actually lift a metal skyscraper filled with fuel, you have to accelerate that escaping gas from subsonic speeds to supersonic speeds.
You need some serious velocity.
Right, and that requires a very specific, iconic piece of hardware. The convergent-divergent nozzle. It's that classic bell shape you see at the bottom of literally every rocket engine.
You literally cannot reach orbit without it. The geometry of that bell is doing heavy, heavy lifting.
This instantly reminded me of the movie October Sky.
Oh yeah, classic.
Which actually gets referenced in the Pavarin lecture. It's the true story of Homer Hickam, this teenager building homemade rockets in a 1950s coal mining town. And he keeps failing. His rockets keep fizzling out or blowing up on the pad.
Because he didn't have the nozzle right.
Exactly. Finally, he studies the advanced math and realizes he needs to machine a piece of steel into this exact convergent-divergent shape. He needs the pipe to pinch inward and then flare outward. But why? What is that specific pinch and flare actually doing to the gas?
It is exploiting something called choked flow, and honestly, it completely defies everyday logic.
Yeah.
Like on Earth, If you're watering your garden and you want the water to spray faster, what do?
You pinch the end of the hose with your thumb?
Right. Constricting the flow speeds it up. That's the Venturi effect. And that works perfectly for the first half of the rocket nozzle, the confluent part. The pipe pinches inward, and the hot gas accelerates faster and faster.
Until it hits the speed of sound.
Which is the crucial boundary, Mach 1. Once a fluid reaches the speed of sound, the physics just flip upside down.
Wait, really? Upside down how?
If you keep pinching the pipe after the gas hits Mach 1, it doesn't go faster. It actually chirks. It creates this massive aerodynamic traffic jam.
Oh, wow.
Yeah, so to force supersonic gas to go even faster, you suddenly have to widen the pipe. You have to give it room to wildly expand. That is the divergent flare of the bell. It channels the explosive expansion of the gas, accelerating it to just mind-boggling supersonic velocities out the back of the engine.
So we are violently throwing supersonic gas out of a specialized bell to move forward. But here is the massive catch, and this is a big one in space. Every single ounce of gas you throw out the back is weight you had to physically carry up there in the first place.
Yep, the ultimate paradox.
You are burning mass to move mass. And this brings us to what might be the single most important metric in all of aerospace engineering.
Oh, the Jolly Roger.
Yeah.
Specific impulse.
Yes. The lecture jokes that if a propulsion engineer is lying on their deathbed, staring at the white light, their final whispered words will be specific impulse.
Is that important?
And if you see a skull and crossbones drawn on an engineering exam, it is a warning. Never forget specific impulse. But what actually is it?
Specific impulse, or ISP, is essentially the ultimate fuel efficiency rating for a rocket engine. It measures exactly how much thrust you are getting for every single unit of propellant mass you consume.
So high IST is good.
Very good. If an engine has a high ISP, you're getting a massive, powerful push out of a very tiny amount of fuel. If you have a low ISP, you're practically dumping thousands of gallons of fuel out the back just to get a tiny little nudge forward. It dictates whether your mission is even possible.
But I need to stop here because reading through the source, I hit another mental roadblock. If ISP is a measure of efficiency and velocity, why on earth is it measured in units of time?
The seconds thing.
Yeah, the metric is always given in seconds. Like an engine has an ISP of 300 seconds or 450 seconds. Why second?
I know it sounds completely counterintuitive to measure fuel efficiency and time, but it was actually born out of a very pragmatic need to solve an international headache.
Oh, really?
Yeah, the velocity is normally distance over time, meters per second or feet per second. But an aerospace engineer in the United States thinks in imperial feet, right? While an engineer in Europe thinks in metric meters.
And in collaborative space programs, mixing those up leads to catastrophic failures. I mean, we've literally crashed multi-million-dollar probes into Mars because someone forgot to convert feet to meters.
Exactly. It's a very real danger. So mathematically, to create a universal metric, engineers take the effective exhaust velocity and they divide it by the standard acceleration of gravity on Earth, known as the G constant.
Okay, the G constant.
Right. Think of G as the baseline pull of Earth's gravity, which is also measured using distance and time. When you divide the velocity by G, you're doing dimensional math.
So the units of distance, whether they're feet or meters, literally just cancel each other out in the fraction.
Exactly. The only unit left standing is time, seconds. It completely strips away all regional bias. A team in Tokyo, Houston, and Paris all know exactly how efficient a 450-second ISP engine is without doing a single conversion.
That is such an elegant mathematical trick. So high ISP means high efficiency, which means you need a smaller, lighter tank of fuel to do the exact same job. The obvious, logical conclusion here is that we should just always use the fuel combination that gives us the highest possible ISP. Right?
I think so.
Like liquid hydrogen and liquid oxygen, case closed. Build every rocket out of that.
You would assume that is the golden rule. But this is where the physical reality of bending metal completely crushes theoretical math, because ISP alone does not tell the whole story.
Right, the deceptive math of scaling and structure. Because we also have to look at impulse density.
Yes. Let's use your example of liquid hydrogen. As a fuel, it is the absolute holy grail of efficiency. It has a fantastic ISP around 450 seconds, but liquid hydrogen is incredibly fluffy.
Fluffy?
Yeah, it has terrible density. It is so physically light and takes up so much spatial volume that to carry enough of it to be useful, you have to build absolutely massive giant metal tanks to hold it.
Oh, so your fuel is highly efficient, but your fuel tank is suddenly the size of a skyscraper, completely negating the weight savings you got from the fancy fuel in the first place.
Exactly. Compare that to the solid rubber rockets we talked about earlier. Solid rockets have a much lower ISP, maybe 250 seconds. Theoretically, there are worse engines.
But they're dense.
Extremely dense. It is heavy, tight, and compact fuel. You can pack a massive amount of explosive energy into a very small tube. This is exactly why military submarines and fighter jets use solid rockets.
Oh, that makes sense.
Yeah, they don't have the physical room for a giant, fluffy hydrogen tank. They need a weapon that fits inside a narrow launch tube, sits in storage for 5 years, and fires instantly. They willingly trade pure efficiency for high density.
Okay, but what about the overall structure of the ship?
The inert mass, right?
Right.
The weight of the metal walls, the valves, the flight computers. If I'm an ambitious startup founder and I want to launch a small satellite that is 100 times smaller than what a massive SpaceX Falcon 9 launches, I'll just save money by shrinking my entire rocket design by a factor of 100. Oh boy.
Right. Just take a big, successful rocket and scale it down linearly on a computer.
This raises an important question. And honestly, it is the exact trap that bankrupts so many aerospace startups.
Yeah.
You absolutely cannot scale physical technology down linearly. The laws of physics, specifically the square-cube law, simply forbid it.
The square-cube law. Break that down for me.
Okay, imagine a full-sized orbital rocket. Its outer metal tank wall might only be 1 millimeter thick to save precious weight. It is practically a metallic balloon held rigid by the pressurized gas inside.
Got it.
Now, you want to scale the entire rocket down 100 times to save money. Does that mean your new tank wall is going to be 0.01 millimeters thick?
Oh, I see. You physically couldn't manufacture metal that thin, and even if you could, it would burst instantly under the intense pressure of the turbopumps.
Right. You still need a minimum thickness just to hold the physical explosion.
Yeah, that makes total sense.
Under the square-cube law, as you shrink an object, its internal volume, which dictates how much fuel you can hold, shrinks exponentially faster than its surface area, which dictates the heavy metal walls you have to build.
Wow.
You still have to build a wall thick enough to not explode. You still need valves that physically open and close. You still need a heavy flight computer. So as you scale the rocket down, the weight of your dead metal structure does not shrink at the same rate as your fuel capacity.
So the smaller you go, the higher the percentage of your rocket is just dead, useless weight.
Exactly. They assume the math shrinks perfectly on a spreadsheet, but the physical metal does not.
It's a brutal reality check. All of these compromises we've talked about, whether you use a dense, solid firework or a highly efficient liquid plumbing system, the Venturi physics of your nozzle, the universal metric of ISP, and the stubborn square-cube law of metal structures, all of it inevitably collides in one terrifying 19th century mathematical equation.
The big one.
An equation that relentlessly governs absolutely everything leaving this planet.
The Tsiolkovsky rocket equation.
Yeah. Konstantin Tsiolkovsky, a Russian scientist living in the late 1800s. And the history here is just wild to me.
Oh, his background is amazing.
Right. He lost his hearing as a child, which kept him out of traditional schooling, so he just isolated himself in a library, taught himself advanced mathematics, and somehow managed to mathematically deduce the precise laws of rocketry decades before humanity ever put a working rocket into space.
It's an incredible story of genius.
He didn't have wind tunnels or NASA supercomputers. He just had theoretical physics in his mind. And the source material refers to the equation he wrote as a Stephen King horror story.
That's a great way to put it.
So what does this all mean? Why is a math equation a horror story?
Tsiolkovsky's equation is a horror story because of one specific, ruthless mathematical function buried inside it. The exponential function.
Oh.
Yeah. The equation dictates the relationship between your rocket's starting mass, its empty mass, and your delta V. Delta V is simply the change in velocity your customer is paying for. Like, I need this much speed to reach Earth orbit, or I need this much speed to reach Mars.
And obviously, to get more speed, you have to burn more fuel.
But the horror is that the relationship is strictly exponential, not linear. If you want to double your speed, you don't just put twice as much fuel in the tank.
Why not?
Because when you add that extra fuel to go faster, your rocket is now physically heavier on the launch pad. So you have to add even more fuel just to generate the thrust required to lift the extra fuel you just added.
Oh, man.
And then you need more fuel to lift that fuel.
It's a compounding nightmare.
Yeah.
You are trapped in a cycle of burning fuel purely to accelerate unburned fuel.
It creates a literal mathematical cliff. If your target destination requires too much speed, and your engine's specific impulse is too low, and your metal structure is too heavy because of the square-cube law, The equation literally breaks.
Breaks.
The
How?
amount of propellant mass required doesn't just get very large, it becomes mathematically infinite.
Infinite math.
It means the mission is physically impossible under the current laws of physics, no
Ugh.
matter how gigantic you build the rocket on the launch pad. The universe just says no.
That's terrifying.
The only variable that saves you, the only light in the dark of that horror story, is specific impulse. In Tsiolkovsky's equation, ISP sits in the denominator of that terrifying exponent. A high ISP is the only mathematical force that tames the exponential growth and allows humanity to actually reach orbit.
It all comes rushing back to the Jolly Roger. Never forget ISP. Because if you do, the math goes infinite, gravity wins, and you stay on Earth.
The entire aerospace industry bows to that single variable.
Unbelievable. So to wrap up this deep dive, we've gone from looking at a rocket as just a big cinematic pillar of fire to understanding the intense chaotic pressure of trillions of particles bouncing inside a naked metal chamber.
Which is mind-blowing on its own.
We've seen how the Venturi effect in a bell-shaped nozzle is the only way to physically break the sound barrier. We've seen how specific impulse is the universal metric of survival measured in seconds, and how the brutal exponential math of a deaf 19th century Russian scientist dictates exactly how far we can travel into the dark.
It's a lot to take in. But if we connect this to the bigger picture, to your daily life, the lesson here extends far beyond aerospace engineering.
How so?
Well, true problem solving. Whether you're trying to build a rocket, launch a new software platform, or reorganize a global supply chain, it's never just about applying a single magic formula. It is about deeply understanding the hidden physical trade-offs.
Right.
It's recognizing that chasing high efficiency might entirely ruin your density and footprint. It's knowing that scaling down a successful system to save money might physically break the architecture.
Yeah.
You have to understand the hard limits of the materials and the math you're working with.
That is a phenomenal takeaway. And that leads to one final thought for you to ponder. We just talked about Tsiolkovsky's horror story, right? That compounding, inescapable nightmare of needing fuel to carry fuel.
Yep.
But that entire equation relies on one fundamental underlying assumption. And that is that the rocket must physically carry its own reaction mass with it off the surface of the Earth. But what happens to that math and to humanity's future in the stars if we figure out a way to break that rule entirely? What if a ship didn't have to carry fuel, but could harvest its mass from the vacuum of space itself as it travels?
That changes everything.
Or what if a ship could ride on a massive beam of laser energy projected from Earth, leaving the impossibly heavy power source safely on the ground? When you look at that pillar of fire and upward motion on the launch pad today, you are looking at humanity fighting a brutal war against physics. But maybe, someday, we won't have to fight the horror story at all. We'll just leave it behind.